Hello everyone, welcome to another video from the tutorial series Aspen Plus Mastery and Certification. My name is Tabish. In this video, we will learn about NIST database, specifically learn about the Thermodata Engine tool, how to retrieve different thermophysical property parameters, and how to perform property analysis. Let's have a brief background about NIST Thermodata Engine, then we will dive into Aspen Plus and explore it in detail. NIST stands for National Institute of Standards and Technology, an agency of the US Department of Commerce with the mission of promoting innovation and industrial competitiveness. This is the official website of NIST. Under Services and Resources section, they have listed different databases, including Chemistry Webbook, National Vulnerability Database, Physical Reference Data, and Standard Reference Data. I invite you to have a look into Chemistry Webbook before we move on to NIST Thermodata Engine. Let's open Chemistry Webbook. NIST Chemistry Webbook is the online portal where you can explore and retrieve different thermophysical properties of a large number of components. Here you can browse the component with name, formula, IUPAC identifier, or the CS number. Let's take an example and browse a component with the name of the component. On this page, you need to enter the name of a chemical species. You can retrieve either thermodynamic data including gas phase, condensed phase, phase change, reaction, ion energetics, or ion clusters, or you can retrieve a large number of other databases. Let's take an example of methanol component and search gas phase and condensed phase as well as phase change properties of methanol. Go to search option. Here you can observe a key information regarding the component also called as methyl alcohol, including the chemical formula, molecular weight, even the chemical structure. You can also browse the 2D MOL file of the chemical structure, isotopologues information of the component, a range of alternative names of the component either used in the literature documents or named commercially. You can also view thermophysical properties of the component, including gas phase thermochemistry data, condensed phase thermochemistry data, and phase change information. Let's browse the gas phase thermochemistry data. The citations of the contributors of this data are also listed. The first information regarding gas phase thermochemistry data is the standard heat of formation of the gas phase methanol. Its corresponding value minus 205 kilojoule per mole is also listed. This value is taken as the average value of 9 different sources. You can browse the individual data points as well. Here are the data points that have been used to take the average value of the standard heat of formation of the methanol, and the value ranges from minus 201 to minus 214 kilojoule per mole. The corresponding literature citation is also provided. Similarly, standard heat of combustion is also provided. An important information of this page is regarding the constant pressure heat capacity of the gas phase. The heat capacity as a function of temperature is provided, and the literature citation is also given. You can browse the available information on this page. The condensed phase thermochemistry data is also provided. The chemistry webbook can be of very much interest for the students and users who does not have directly access to Aspen physical property database or want to have a very quick access to the thermophysical data of any desired component. I invite you to explore it further so that you have an alternative source to browse the thermochemistry data of your desired component. So let's go back to the database of our interest for today's discussion, and the relevant data source is the standard reference data. Regarding standard reference data, you can see different data products provided by National Institute of Standards and Technology, and those products include RefProp, representing reference fluid thermodynamic and transport properties, mass spectral library, NIST Inorganic Crystal Structure Database, NIST Thermodata Engine, and so on. Let's explore NIST Thermodata Engine. The actual power of Thermodata Engine lies in the availability of the experimental database that is currently developed and maintained by Thermodynamic Research Center of NIST. The NIST TRC source data archival system currently stores more than 4.8 million experimental data points that includes experimental thermophysical and thermochemical property data. Besides thermophysical properties of the pure components, there are more than 4,000 calorimetric values of different reactions and reaction equilibrium data of more than 1500 reactions. Also, the NIST archival system contains a large number of data points for the multi-component systems. For instance, the single-phase and multi-phase thermodynamic and transport property data of more than 40,000 binary mixtures and 11,000 tertiary mixtures is present in the archival system, and Thermodata Engine provides a comprehensive and critical evaluation of the data points for the estimation of different thermophysical properties and property parameters. The Thermodata Engine tool is integrated in Aspen Plus and Aspen Physical Property System, so you can imagine the power of Aspen Plus and Aspen Property System for the estimation of different properties and parameters that is required for the property analysis and process simulation. This is beyond the scope of current video to discuss how critical evaluation of the experimental database is performed by Thermodata Engine. However, we will explore in Aspen Plus interface how can we retrieve the experimental data points and perform property analysis based on the experimental data points. So let's dive into Aspen Plus interface for further discussion. Let's create a new simulation without any template. Add water and ethanol as the target components. Let's have a look on the enterprise database. You can notice all available databanks in the Aspen Physical Property System on the left and selected databanks on the right. The default selected databanks includes Pure 40, aqueous, solids, inorganics, APUS and NIST TRC. NIST TRC databank is developed based on the thermochemistry data as compiled by Thermodynamic Research Center of National Institute of Standards and Technology. Let's have a look what is the difference between NIST TRC and Pure 40 databanks. Go to help option, search for NIST TRC. You can notice the NIST TRC databank as the third search result. Let's have a look. The NIST TRC databank contains pure component data for 33,989 compounds, mostly organic compounds, and this includes approximately 2,000 compounds that are available in the main pure component databank named as Pure 40 for Aspen version 14. The property parameters and experimental data in this databank were collected and evaluated by the Thermodynamic Research Center of NIST using NIST Thermodata Engine and the experimental data stored in the source data archival system for the experimental thermophysical and thermochemistry property evaluations. You can also notice the databank parameters. You can notice both scalar properties as well as temperature property parameters in this table. The mathematical correlations used for the estimation of property parameters are also mentioned in this table that has been evaluated by Thermodata Engine. For instance, ideal gas heat capacity property parameters has been estimated by Thermodata Engine using LLE model. Similarly, the heat of vaporization has been estimated by Watson equation. Bracket parameters for the liquid molar density. Somewhere polynomials has been used for the estimation of property parameters. PC Soft's model is also used. So you can browse the corresponding mathematical correlation that has been used by Thermodata Engine for the estimation of property parameters. You have three different ways to retrieve the thermophysical properties and parameters information from Aspen Plus. One of them is NIST TRC databank that contains experimental information of a large number of pure components and multi-component systems. The other two ways depend on the selected databanks in the order of their presence in this window. Let's first explore the data retrieval from NIST TRC databank and then we will move on to two other ways. So for NIST, go to this NIST Thermodata Engine Under Data Sources in the Home tab, a window pop-ups that suggests whether you are interested in the property data of pure component or binary mixtures or the ternary mixtures. Let's first have a look into the pure component property data. For the sake of example, let's select pure water. You can evaluate the properties from here. The corresponding properties and parameters has been retrieved successfully. The retrieved properties are grouped into relevant categories, including eccentric factor, critical properties, energy of formations and vaporizations, other scalar properties including molecular weight, normal boiling point, specific gravity, triple point of temperature, and some of them are the temperature dependent property parameters. Let's have a look on the ideal gas heat capacity values. Ideal gas heat capacity values have been evaluated by Thermodata Engine using LLE ideal gas heat capacity model. You can see the parameter values over here. These property parameter values has been regressed through the experimental data that is listed in this table. You can see the ideal gas heat capacity values as a function of temperature, and the literature citation for each and every value is also given. For instance, the first value is taken from this reference. Based on the LLE model, the evaluated results are also presented. You can see the evaluated values of ideal gas heat capacity from 50 Kelvin to 5000 Kelvin. You can export these values externally from the clipboard. Similarly, you can also browse the vapor pressure data. First, have a look on the experimental data of vapor pressure of water. You can notice that the vapor pressure information in the units of Newton per square meter as a function of temperature has been retrieved, and in total there are 2418 different data points retrieved from the literature at different temperatures. You can notice the literature citation against each data point. So based on these experimental values, Wagner 25 model has been evaluated by Thermodata Engine for the liquid vapor pressure property parameters. Those property parameters are displayed in the values column with corresponding unit. So using these property parameter values, the predicted values and evaluated results are presented in this table. The same way you can explore other pure component properties and property parameters. If you are interested, you can save these property parameter values. Aspen asks whether you want to display the property values right now, and you can notice under the method section, in the parameter section under pure components, all the property parameters are stored. The scalar properties are grouped in the TDE1 tab. You can notice all the scalar properties over here, and the temperature dependent property parameters are displayed in a corresponding tabs. This is how you can retrieve the pure component information from NIST Thermodata Engine. Similarly, you can retrieve the binary and tertiary component properties. For instance, let's retrieve the binary mixture properties and parameters. So select both of the components and retrieve the data. So the retrieved information is provided in the TDE results tab. The properties corresponding to the binary mixtures are stored in the couple of folders, including the azeotropic data, binary vapor liquid equilibrium data, similarly the critical density data, molar volume and density information of the binary mixtures, eutectic temperature, excess enthalpies, heat capacity at constant pressure, thermal conductivity, viscosity, and so on. All this information is related to the binary mixture of ethanol and water. So let's explore the isobaric vapor liquid equilibrium data of binary mixture. So in this tab isobaric, under binary vapor liquid equilibrium, you can see all the experimental information regarding isobaric vapor liquid equilibrium data is presented in this table, and in total 86 different data sets are presented here. Against each data set you can notice the number of points. Had the number of points in any of the data sets represents the resolution of the data points, the year of publication of the data, temperature range, corresponding pressure at which the experiment was performed is also listed. So let's take an example to view how this data of binary vapor liquid equilibrium at constant pressure looks like. So let's consider VLE003 dataset that contains 60 points that was published in 1901, and experiments were performed between a temperature range of 351 to 372 Kelvin at almost 1 atmospheric pressure. So let's go to the dataset VLE003. You can notice the literature citation of the dataset and all the data points in this dataset, and in total that contains 60 data points ranging from 0.998 mole fraction of water to the 0 mole fraction of water. So it's almost in between pure water and pure ethanol. If you want, you can plot temperature XY plot of this dataset as well. So you can notice that the retrieved dataset from this reference only includes the bubble point curve, and the dew point curve in this dataset is also missing. Before using any of the dataset, it is also advised to run the consistency test so that you are sure about the quality of the dataset. For that purpose, you need to go to the consistency test and simply you need to run the consistency test over here. Aspen gives the warning that this may take a few minutes, so we are okay with this. So the consistency test has successfully run. Aspen Plus evaluates the dataset using different consistency tests including Harrington test, oneness test, point test, infinite dilution test, US test, endpoint test, and so on, and the overall evaluation from different tests is represented by overall data quality. Any dataset that has the overall data quality close to 1 or equal to 1 is considered as the highest quality dataset. You can align all the dataset in a descending order so that the highest quality datasets are presented at the top of the table. So at the top, all the datasets that are sufficiently good with the consistency are presented at the top and relatively poor datasets are presented at the bottom. You can notice the bottom data points that has the low overall data quality value has failed couple of the consistency tests, whereas the datasets at the top has successfully passed most of the consistency tests. As a first choice, you can use the dataset that has overall high quality and it contains higher number of data points so that the quality of data and the resolution of data both are reasonably well for further evaluation. So for the given situation, the dataset labeled as VLE068 may be considered a reasonable quality data for further processing because it has the highest data quality and number of points are also reasonably well. To view this dataset, go back to experimental data and dataset VLE068. If you prefer, you can plot TXY chart of this dataset. Here you can view the bubble temperature and the dew temperature curves as a function of the mole fraction of the water component. If you prefer, you can copy this data to the clipboard and export externally to use in other applications. This is how you can retrieve the thermophysical properties and property parameters from NIST Thermodata Engine. If you are interested, you can save the experimental value in the current simulation for further use. To save, either you can select only the current dataset, that is VLE068, or you can select all the data points. Let's only save VLE068. Aspen asks whether you want to save the data and view it as well. So here you can notice that the selected values are saved under the data tab in the navigation pane. If you want, you can also rename the data for your memory. We will come back to the same data points during property analysis, but first have a look what are two other different ways to retrieve the thermophysical properties. So for that, again go back to the component specification tab under the selection of the components. The other two methods are either using the review option from here or the retrieve parameters in the tool group. So you can notice both of the tabs are currently inactive. These two options will be only active if you have specified the thermodynamic property method. For the sake of current example, let's select an RTL property method. Once this is selected, go to the next option and you can notice that immediately retrieve parameter option is active. Similarly, the review option is also active. So both review and retrieve parameters take the information from the enterprise databanks in the order of the sequence they appear in the selected databanks. So if the components are found in the pure 40, then the retrieve parameter option and the review option will retrieve the information from the pure 40. Otherwise, it will go to the next databank and next databank and so on. In case the given components and the corresponding properties are not available in any of the databank, then the Aspen Plus will fail to browse and show the property informations. So let's go to the selection and first have a look on the review option. This review option only retrieves the information of the pure components, whereas the retrieve parameter retrieves the information of the pure components and the multi-component mixtures as well. So let's retrieve the information of the pure components first. So all the properties related to the pure component is listed under the same method section in the pure components. For instance, you can notice that for the heat capacity information you have CPI ALE as well as CPIG DP. So the CPI ALE has the source as user, and the CPI-ALE is the ideal gas heat capacity retrieved by Thermodata Engine using ALE ideal gas heat capacity model. Whereas the CPIG-DP, the source for this information is DB Pure 40, that indicates that these property parameters are obtained from Pure 40 data bank, and this is the same ideal gas heat capacity coefficient parameters for the Dipper ideal gas model. Let's retrieve the same information using retrieve parameter option. Aspen notifies that you can view the results on the property parameters results form. Whether you are interested to copy the pure component property parameters to the inputs, let's copy the property parameters. Whether you are interested to view the results, yes. So the property parameter information is provided in the results section under property parameters, and the same information is copied to the pure component property parameter informations. You can notice couple of other property parameters has been added to the pure component property section that were not present in case of the property retrieval using the review option. Now the property information includes, you can notice the retrieved information for the pure components as well as binary interaction parameters, specifically the temperature interaction parameters for the corresponding property model. So this is how you can use three different ways to retrieve the experimental property and property parameters of the pure components and multi-component mixtures. So once you are fully aware of how to retrieve the properties and property parameters using three different ways as we discussed, so now we can learn how to perform property analysis. For the property analysis, go to this analysis section. Either you can perform pure component property analysis as a function of temperature and pressure, or you can perform the binary analysis, specifically generating Tx5, Px5 or Gibbs free energy of mixing curves for the binary system. Alternatively, you can perform mixture property analysis where you can analyze the thermodynamic and transport properties as a function of independent parameters, for example temperature, pressure and the mixture composition. Further, you can perform solubility analysis or the pressure temperature envelope as well as ternary diagram for three components and the residue curves. Let's first explore the pure component property analysis. For the property analysis, you have to have the property method defined under the method section. You can perform the property analysis based on the thermodynamic properties or the transport properties, or you can perform equation of state alpha function test. So let's choose any thermodynamic property. For instance, constant pressure heat capacity of the pure component. You need to select the units. Let's take the unit of kilojoules per kg per Kelvin. You also need to specify the phase of the component, either the vapor phase or the liquid or the solid phase. Let's go for the liquid phase so far. Also, you need to specify which component property analysis you want to perform. Let's select water as of now. So once all this information is provided to the property analysis function, immediately it gives the option to run the analysis. So this analysis will be performed for the heat capacity of the pure component water as a function of temperature. You can change the unit of the temperature if you prefer. You can change the pressure of your desired pressure where you want to perform the property analysis. The temperature for this analysis will be between 0 and 100 degrees Celsius, and in total there will be 50 points evaluated between 0 and 100 degrees Celsius. Besides equidistant analysis, you can specify the independent parameter axis as logarithmic axis, or you can specify the individual values where you want to perform the property analysis. Let's go with the equidistant analysis. You are ready to run the analysis. So once the analysis is successfully run, you can notice the heat capacity of water as a function of temperature is provided. You can follow this curve to notice the heat capacity value at any temperature between 0 and 100 degrees Celsius for the liquid phase. Even here you have the option to change the units for the both axes. Further, if you want to look into the heat capacity value at any specific temperature, you can open the show tracker. It will automatically highlight the tracker on the curve. So here you can drag the tracker to any temperature. For instance, at 40 degrees Celsius, the heat capacity value is 16,586.79 kilojoule per kg per Kelvin. You can move the tracker on the curve so that you can notice the value at your desired temperature. You can remove the tracker, go back to the show tracker and just uncheck it. You can also notice other options. You can zoom in, zoom out, or zoom full depending upon the requirements. You can also add any text to this graphical representation, whether you want to display the legend or not, or if you want to edit the legend value. Besides, there are a couple of options where you can fine-tune the graphical presentation of this information. For instance, if you would like to have a very square plot between the two parameters, you can use the square plot. If the axis seems to be highly occupied with the numbers, you can change the grid scale. For that purpose, just double click the axis values and a new window will pop up where you can change the grid interval. For instance, let's change the interval from 25 to 50. It will automatically shift the interval to 50. This is how you can also change the grid scale of the x-axis as well. You can also play with the fonts, for example with the font size, or whether you want to make the bold or italic, or you are interested to change the font type, or you can play with the other options that can be used for better graphical presentation. So besides heat capacity, you can scroll other thermodynamic properties as well as the transport properties, for instance the thermal conductivity or the viscosity and so on. Besides, if you are interested, you can also view the numerical results values. You can copy the numerical values in the clipboard and export to any external software for better graphical presentation. Let's have a look into the binary component analysis. Go to the binary component option. Here the binary component analysis is only restricted to TXY, PXY or Gibbs free energy of mixing curves for the binary system. Let's open the binary component analysis. Like pure component analysis, here are different possible analysis that you can perform for the binary system. The components are listed here. You can select the basis of the composition. Let's stick to the mole fraction composition. Whether you want to vary the water composition or the ethanol composition. You can limit the composition, starting and end points for the analysis, also the number of intervals, and also you can adjust the pressure at which you want to perform the analysis. So once you are okay, you don't need to do anything else. You can simply run the analysis. The TXY analysis of the binary system is successfully performed. You can notice the dew curve in the green and the bubble curve in the blue. This analysis has been performed by the NRTL method. You can observe that the water ethanol mixture does not form an ideal solution, and the NRTL method has also calculated the TXY diagram for the non-ideal system. In this region, you can consider that an azeotrope has been formed. Besides TXY analysis, you can also perform PXY, TXX, TXXY, PXXY and the Gibbs energy of mixing analysis. You remember we have also retrieved the experimental information of the binary mixture as the isobaric vapor liquid equilibrium data from the NIST, and that data is stored under VLE068 in the data tab. You can also plot the TXY chart from the experimental data. So go to the data section. Here you can notice that all the data points for TXY chart at constant pressure of 101,000 Newton per square meter are available in this table. Let's plot this chart as well. Go to the plot section and the TXY plot. So here is the experimental data for the isobaric vapor liquid equilibrium, and here is the simulated TXY diagram for the same system using NRTL method. We can merge the two plots, experimental and the simulated, using NRTL method. For merging the two plots, you have to have the same axis and the units. Also, the data analysis should be performed at the same pressure as the pressure of the experimental data. Since the experimental data was retrieved at 101,000 Newton per square meter, so we should run the binary analysis at the same pressure. So let's go to the analysis again and fix the pressure first and define the pressure as the same as the experimental data point was retrieved. Shift the units to the units of experimental data set. So run the analysis again. Change the units of the temperature scale. Since the temperature scale of the experimental data was in the Kelvin units, so we have the liberty to change the units of the analysis. So change it to Kelvin. Now we can merge the two plots since the axes for the two plots are the same. Go to the merge plot option. Here you can merge the existing plot of the analysis with the plot of VLE068 TXY plot. Just merge the two plots. Further, you can slightly fine tune the presentation. For that purpose, one of the option is to fix the same scale for the two graphs. For that purpose, just right click, go to the y-axis map, open the y-axis map, and here it gives the option to merge the two axes on a single y-axis. and close this window. So the two axes having the same units and the data analysis performed at the same pressure conditions as the pressure condition of the experimental data was. Now we have the experimental and simulated curves on a single plot where you can compare the experimental and simulated curves. You can notice that the experimental and simulated TXY charts almost overlap each other. That indicates the accuracy of the selected method and corresponding property parameters. We will have a further discussion on the same charts where the selected method is not very much appropriate to simulate the binary systems, so that you can fix the property parameters by regressing through the experimental data. So as of now, you can close these tabs and go to the binary analysis option again. You can also browse other tabs from this binary analysis section, especially the calculation options where you can fix the valid phases or the number of iterations or the error tolerance. Similarly, if you have defined other property methods as well, then you can choose another method. Also, the calculation approach, whether the true components or the apparent components. This is specifically important for electrolyte systems. More importantly, you can go to the results tab where the numerical values of the TXY analysis are available. You can export these values by copying to the clipboard for further analysis and graphical presentations. This is how you can perform the binary analysis. For the binary analysis, we have only very limited options. For the vapor-liquid equilibrium analysis, Aspen also allows to perform the thermodynamic and transport property analysis of your choice for the multi-component systems. For that purpose, go to the mixture analysis. Here you can define the components. You can define the compositions in terms of, let's say, the flow rates. Aspen Plus will automatically calculate the molar fraction. For the property analysis of your choice, you can define the property either from here as a new property, or you can go to the navigation pane in the property sets. Here you can define the property. Let's say we are interested in the heat capacity of the mixture at the desired composition. You can browse from the drop down button. You can notice there is a comprehensive list of the available properties that you can analyze with respect to the independent variables. It can be a very trivial job to search and select the desired property. Alternatively, you can search from here. A new dialog box will open where you can search the property. For instance, the heat capacity. If you prefer, you can limit the search to the pure components, exclude petroleum correlations. As of now, since we are interested for the heat capacity property evaluation of the binary mixers, you have the options of ideal gas heat capacity of the mixer or the heat capacity of the mixer at real conditions. For the sake of this exercise, let's analyze the heat capacity of the real mixer. Click OK. And the heat capacity as a physical property will be added in the property set. So go back to the mixer analysis. You can notice that the heat capacity is immediately available for the properties to analyze. Shift the property to the selected property. Similarly, if you are interested for any other property, you can add from here as well. For instance, the heat capacity of the ideal gas mixture. It will open the same window where you can find the property. Here is the ideal gas heat capacity of the mixture. You can enter the property in the selected window as well. You can perform this analysis with the manipulated variables that includes temperature and the corresponding composition at the given pressure. So let's run the analysis when you have the fixed composition of equimolar water ethanol mixture. We are okay with the temperature conditions and the number of intervals as well as the pressure. So run the analysis. Aspen property system has estimated the ideal gas heat capacity as well as the real heat capacity of the binary mixture. You can notice the real heat capacity of the mixture in the blue color and the ideal heat capacity for the vapors in the green color. Also, you can notice the heat capacity immediately drops in the temperature interval of 75 to 85 degrees Celsius. This is the interval that exists between the bubble point and the dew point for the mixture of given composition. Also, you can notice the vertical axis values where one axis has been defined for each of the property you have analyzed. Similarly, you can perform other property analysis. In any case, you need to define the property first in the property dataset either through the navigation pane or directly you can enter the property from here. So let's scroll. What are other possible properties that you can analyze? It is recommended that you only add one property under one category. If you have another property for the analysis, it is suggested you add another property in the property sets. You can also have a look in the qualifier. That is very valuable option when you are defining multiple properties and especially fixing the property regarding the phase of the system or the number of components, or you want to define the base component or the component groups and so on. We will explore this feature in the future videos. Let's see what other properties are available. Remove the heat capacity from the search bar so that all the properties are available. So the available properties are for the pure components as well as for the mixers, including energies, phase fractions, bubble point temperature, dew point temperature, liquid density, reduced conditions, compressibility factor, activity coefficients, K values, fugacity coefficient, standard volumes, enthalpy information. There is a comprehensive list. These are all the properties that are estimated by different thermophysical property correlations, and Aspen physical properties make the choice of the corresponding thermophysical property depending upon the defined physical property method. This is a very quick tour how to perform the property analysis using pure component, binary component, or for the mixers for any desired thermophysical or the transport property. In the future videos, I will focus more on the other options of the property analysis, including solubility, pressure, temperature, envelope, especially when talking about the phase separation problems, for instance the vapor liquid separation. Similarly for the ternary systems and the residue curves when we will explore the distillation problems. For further practice, I recommend following exercise. Consider a mixture of acetone, methyl ethyl ketone and hexene. So you are asked for how many binary pairs NRTL and Wilson methods contain binary interaction parameters. Does the NIST Thermodata Engine contain isobaric vapor liquid equilibrium data for methyl ethyl ketone hexene mixture? What is the azeotropic composition of acetone hexene mixture at 101.4 kilopascal for acetone MEK binary mixture and using default binary interaction parameters? Which of the following method fails to identify the azeotropic mixture, NRTL or Wilson method? And the last question is, for equimolar mixture of acetone MEK hexene at 1 bar, what are the bubble point temperature values predicted by NRTL and Wilson methods? In the next video, we will explore ternary diagram option under analysis of ternary mixtures, how to perform property estimation of the missing parameters using molecular structure and the limited experimental data, and how to perform regression of model parameters using experimental data.